So I want to introduce you to a new way of thinking about structure and bonding when it comes to predicting shapes, predicting Lewis structures, predicting bonding environments, and predicting hybridization states from the valence bond theory. And I call this technique ODEC. And I would like to give you a few examples of how it works. So I'd like to look at carbon, I'd like to look at oxygen, I'd like to look at sulfur. With ODEC, which stands for orbital diagram electron configuration, we're only going to consider the valence electrons. So with carbon, which has 4 valence electrons, we have 2s2 and we have 2p2, where one is a 2px and one is a 2py. Now with this nomenclature, anytime you have a lone arrow, this is a potential bond. So if you want to know how many bonds that an atom is capable of making without hybridization, then you simply count the number of lone electrons. So in carbon, you see 1, 2 bonds. If you see paired electrons, then of course this is the familiar lone pair. And notice in carbon, in the ground state, there is 1 lone pair. Anytime an orbital is empty, it's going to be an area where there is no electron density. So in this particular example, carbon has a lone pair. It's capable of making 2 bonds. And there's an empty p orbital, so imagine a lobe coming out of the plane, imagine a lobe going into the plane. This is a special type of carbon, a very reactive form of carbon called a carbene. And we will talk about carbenes when we address addition reactions of carbenes to carbon-carbon double bonds or alkenes. Linus Pauling realized that there was a major problem with the quantum theory in terms of relating it to chemistry. And so he proposed 2 ideas. One idea is that of hybridization. And the idea of hybridization is that within the same principal quantum number, so I'm going to simply redraw carbon's ground state electron configuration. Again, I'm ignoring the core electrons. And I will show you a shortcut for being able to predictably do this every time. So in the ground state, I have a 2s2 and a 2p2. Pauling argued that within the same principal quantum number, we could invoke a bit of energy. So energy is applied, probably through a molecular collision, to promote one of my 2s electrons to fill the empty 2pz orbital. And so if this occurs, then rather than having 2 lone electrons, we are going to have 4 lone electrons. And now carbon is capable of making 1, 2, 3, 4 bonds. These 4 bonds will be made no matter how we choose to mix the orbitals. So hybridization is a 2-step process. Step 1 is electron promotion. Step 2 is orbital mixing. With electron promotion, we can make more bonds. And with orbital mixing, we can make stronger bonds. In other words, the initial energy that we input into the system is more than paid back. In fact, we end up earning an energy profit by making more bonds and by making stronger bonds. And in a separate podcast, I'm going to discuss how this hybridization process can be one of 3 ways for a carbon atom. Let's look, however, at the other 2 examples, oxygen and sulfur. Oxygen would be 2s2, 2p4. Remember from Hund's rule, we have to have all of the degenerate orbitals, that means equal in energy orbitals, contain 1 electron before pairing can occur. And so there's really no driving force for hybridization because there's nowhere to put an electron that is going to give me more bonds. In other words, if I were to promote the 2s to the 2p, I would still have 2 bonds and 2 lone pairs. So it does not hybridize. Oxygen does not hybridize. So we can now talk about a bonding environment. A bonding environment is how many bonds can be made. Carbon can make 2 or 4. 2 when it does not hybridize, 4 when it does hybridize. Oxygen can make 2 only. Let's take a look at sulfur in a bit more depth. Again, sulfur is very, very similar to oxygen. In fact, they are in the same group on the periodic table. And let's talk a little bit about how you can use your periodic table to predictably and confidently draw these orbital diagram electron configurations. So on the second row of the periodic table, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and we'll make these the noble gas. This last column will be our noble gases. This would be neon, argon, krypton. Of course, we'll have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. Hybridization is possible on the second row of the periodic table if you have an empty orbital. So beryllium and boron and carbon are all capable of hybridization because beryllium has a 2p orbital with no electrons. Boron has a 2p orbital with only 1 electron, and carbon has a 2p orbital with only 2 electrons. Now, a lot of people are going to be intimidated by the fact we're talking about electron configurations. This is a fundamental tenet of the quantum theory. You were introduced to the quantum theory in Gen Chem 1. It is my expectation that you know electron configurations very, very well in order for ODEC to work. If you do not, refamiliarize yourself, remaster it, or you're going to have a lot of discomfort as we go through the structure and bonding modules. So let me just show you how it works for these three elements quickly. So beryllium, in terms of its valency, you're on the second row. So just count the S's. 2s1, 2s2. 2 arrows. Nothing in the 2p. I can hybridize beryllium by promoting one of my 2s electrons to the 2p. I go from making 0 bonds, if it's not hybridized, to 2 bonds. Now I'm not showing the orbital mixing at this point, but if I take one 2s orbital and I mix it with one 2p orbital, I get 2sp and 2 unhybridized p orbitals. So the hybridization is sp2p. Notice there are 1, 2, 3, 4 bonding orbitals before I mix. There are 2, 4 bonding orbitals after I mix. Now I'm going to change this for just a moment to reflect boron. Boron would be 2s2, 2p1. And of course I can hybridize boron as well. Before hybridization, boron can make 1 bond. After hybridization and mixing, boron can make 3 bonds, and the hybridization, I'm going to put this one in red, I will have 3 sp2 hybridized orbitals, but 1 unhybridized p orbital. Again, 1, 2, 3, 4 bonding orbitals before hybridization and mixing, and I have 4 after. So boron without hybridization makes 1 bond. Boron after hybridization makes 3 bonds. So the genius in Pauling's hybridization model is that it would accurately predict the number of bonding environments we find in beryllium and boron and carbon in nature. So let's talk about some cardinal rules of organic. Carbon prefers to make 4 bonds. They could be 4 single bonds. They could be 2 single bonds and 1 double bond. There could be 2 double bonds. Or I could have 1 triple bond and 1 single bond. This gives rise to an awful lot of molecular diversity. So you could have alkanes, alcohols, alkyl halides. You could have aldehydes, ketones, carboxylic acids, alkenes. You could have allenes. You could have alkynes. They can be branched or linear. They can be in rings. They can be aromatic. So carbon is the center of the organic universe, which is why it's the only element on the periodic table to have its own discipline. So now that we've looked at this, let's take a look at sulfur. And for sulfur, we're in the 3rd row. So we have 3s, 3p, but the 3rd row of the periodic table also has unfilled d orbitals. And if you're rusty on this, I would strongly encourage you to re-evaluate the off-ball principle. In other words, when n equals 1, there's only a 1s orbital. When n equals 2, we can have a 2s orbital, and we can also have a 2p orbital. When n equals 3, we can have a 3s orbital, a 3p orbital, or a 3d orbital. By now you should clearly see the pattern. In n equals 4, there's a 4s, there's a 4p, there's a 4d, and there's also a 4f. This is about as far as we need to go in the periodic table. So what we can do now is do the order of filling. So you're going to draw a set of diagonal arrows where the tail is to the upper right and the head is to the lower left. And we're just going to follow tail to head, tail to head, tail to head, and we can begin to write these electron configurations. You can also use your periodic table and just count the electron configurations. So based on off ball, we would have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4d, etc. Remember, in each s orbital, you can have a maximum of 2 electrons. In a p orbital, you can have a maximum of 6 electrons. In a d, you can have a maximum of 10 electrons. And in an f orbital, you can have a maximum of 14 electrons. So to take this even further, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 4d10. That will take us up to atomic number 46, which is more than enough in organic chemistry. Also, let's say for a moment we wanted the electron configuration for sulfur. Now, sulfur has an atomic number of 16. So here's my 1 row, my 2 row, and my 3 row. ODEC only wants the valence electrons, so I'm not going to worry about 1s2 or 2s2 or 2p6. So these are already assumed to be there. These are core electrons with respect to sulfur. What I do worry about is the 3s2, which I already have. And that takes me up to 12. I only need 4 more electrons, so I don't have to use all of the 3p's. But when n equals 3, when I'm on the 3rd row, these 3d orbitals are available. So let's talk about bonding environment number 1. Like oxygen, which shouldn't surprise us, we have the potential to make 2 bonds with 2 lone pairs. So sulfur can make 2 bonds and have 2 lone pairs of electrons. If we hybridize once, we can hybridize the 3p, one of the 3p electrons to the 3d orbital. And now I can make 4 bonds and have 1 lone pair. I can do this again. I can promote one of my 3s electrons into the 3d. And now I can make 6 bonds with 0 lone pair. In other words, sulfur could exist as SF2, as SF4, or as SF6. I'd like to focus on how we can draw the Lewis structures for these 3 molecules using ODEC. So when no hybridization occurs, fluorine is going to make 1 bond because it only has 1 unpaired electron, and of course fluorine is a 2nd row element that is not capable of hybridization. Therefore, the sulfur atom, we already know, will have 2 lone pairs. And we'll have 2 bonding pairs. If you look at the electron configuration of sulfur, we have a 2s2 and a 2p7. 1, 2, 3, 4, 5. 2s2, 2p5, 7 valence electrons. Fluorine is capable of making 1 bond, which it is, and it has 1, 2, 3 lone pairs. I can draw these as lines or as electrons, whichever you prefer. And this is the proper Lewis structure for SF2. It will be in the tetrahedral family. And it has a molecular geometry referred to as bent, which means it will be a polar compound. If we were to complete the parallelogram, basically I'm going to draw in blue a dashed blue line that's parallel to the opposite bond, and the same over here. And the overall dipole will extend from the central atom to where the parallelogram meets. So here's my overall dipole moment. You can do this with water. If you take a glass stirring rod and the glass stirring rod approaches a drop of water coming from a faucet, the water will actually bend around the rod, which is evidence that it is a bent molecule. So like water, SF2 is going to be a bent molecule. Let's now look at SF4. So with SF4, again, I have a 3s, (3s2), 3p4, just like I had in the beginning, but now I'm going to promote an electron and mix some orbitals. So I'm going to promote my 3px into an empty 3d orbital. Now sulfur can make 4 bonds and have 1 lone pair. This is 5 areas of electron density. So this is in the trigonal bipyramidal family. And this shape is seesaw. And of course, each fluorine has 3 sets of lone pairs. We've already seen this. The nice thing about ODEC is it's very easy to predict this behavior. You don't have to do the math every time. People that are intimidated by ODEC don't remember their quantum mechanics, and you can't forget your quantum mechanics. So in a trigonal bipyramidal system, you would have, you want to imagine that we've taken this trigonal planar and rotated it into the plane of the screen. So all of these are 120-degree bond angles, and then you're going to have one that comes straight up and one that goes straight down. And so one of these at 100, one of these equatorial positions, if you will, is occupied by the lone pair. And here's the fulcrum of your seesaw. And here are the ends of the seesaw on which you would sit. So this is seesaw. It is polar. These are questions I expect you to answer on any type of problem I could ask you on your test. So as an exercise for homework, what about SF6? Draw its Lewis structure, predict its geometry, predict its polarity. Some other things to consider. How many bonding environments exist for fluorine, chlorine, selenium, silicon, carbon, nitrogen, phosphorus. By bonding environments, let's tackle the first one. There's only one. Fluorine makes one bond with 3 lone pairs. That is one bonding environment. We've already seen sulfur. Sulfur has 3 bonding environments. 2 bonds, 2 lone pair, 4 bonds, 1 lone pair, 6 bonds, 0 lone pair. Very fundamental question to ask about ODEC, a question I expect you to be able to answer on your first exam. Second question, does NF5 exist? Justify with ODEC. Or I could make a claim such as OF4 does not exist. Why? Explain with ODEC. So these are some issues I expect you to be able to handle for your first exam, which will be on Wednesday. So I will pick up the next podcast with some more of these basic questions about ODEC and try to take you through some more solutions. But I do want you to consider these 2 questions and also to answer those questions about SF6.